Hello everyone. In this video, I'm going to talk about initial topology generated by a family of mappings. This is a very important topic because it provides the framework for defining many important structures in general topology and also in functional analysis, such as the product topology, the weak topology, and the weak star topology. Let's get started. Let X be a set and let Y alpha tau alpha be a non-empty family of topological spaces. For each alpha in I, we consider a function f alpha from X to Y alpha. So over here, this is X and these are spaces Y alpha. We are interested in defining the weakest topology tau on X such that every function f alpha from X with topology tau to Y alpha with topology tau alpha for alpha in I is continuous. Obviously, if we equip X with a discrete topology, then every function f alpha from X to Y alpha is continuous. How come that is true? Because in X with a discrete topology, any subset of X is open. Okay, so if we take any open set U in Y alpha and you take its inverse image under F alpha, it is a subset of X and therefore it is an element of the discrete topology. So it is open in X with the discrete topology and therefore F alpha is continuous. Nevertheless, the discrete topology is the strongest topology on X, and again we are interested in defining the weakest topology on X such that every function f alpha for alpha in I is continuous. How can we construct such a topology? Let's consider our next slide. Okay, um, suppose that tau is the weakest topology on X such that every function f alpha is continuous. Okay. Then if you take an open set, say U alpha 1 in Y alpha 1, and then take its inverse image under F alpha 1, then we have this set. And because we assume that F alpha 1 is continuous, this is an element of the topology tau. More generally, if you take three open sets, U alpha 1 in Y alpha 1, U alpha 2 in Y alpha 2, and U alpha 3 in Y alpha 3, and then take their inverse images under f alpha I for I from 1 to 3 and then form this intersection. So these are three open sets in X with the topology tau. So its intersection belongs to tau. Okay. And it is similar for the case where we take finitely many open sets in Y alpha and take their inverse images and form this intersection. Okay, so we define the following collection of subsets of X. Each element of B is a finite intersection of inverse images of open sets in U in Y alpha. Okay, and it turns out that B is a basis for the weakest topology on X such that every function f alpha is continuous. We are going to see that in the next slide. Okay, now we consider the collection B given by B is the intersection for I from 1 to m of f alpha I inverse of u alpha I. Here, u alpha I is open in y alpha I is in I, and m is any positive integer. Then B is a basis for a topology tau on X, and it is the weakest topology on X, such that every function f alpha for alpha in I is continuous. The topology tau is called the initial topology on X, generated by the family of mappings f alpha for alpha in I. How can we prove this theorem? Please see my previous video on topology generated by a collection of sets in the description below in order to know how to prove this theorem. Okay, so we are going to show that both of the conditions mentioned in that theorem are satisfied. First of all, we're going to fix any x in X and show that X belongs to some element of this collection. So we're going to take any alpha naught in I and see that X belongs to the inverse image of y alpha naught under f alpha naught, which is X because f alpha naught is a function. This is always true. And because y alpha naught is an open set in the topological space y alpha naught, we see that X belongs to this set, and this set is an element of B by its definition. In this case, M is equal to 1. So the first condition of the theorem I mentioned is satisfied. To show that the second condition is also satisfied, we are going to take V1 and V2 in B and take any X in this intersection. Our goal is to show that there is another set W in B such that X belongs to W and W is a subset of this intersection. Because V1 is in B is a finite intersection of inverse images of open sets in Y alpha. Similarly, V2 also has the same structure. It is easy to see that V1 intersection V2 also belongs to B. So let W be this intersection, then W belongs to B, and X belongs to W, and W is a subset of this intersection. In this case, we have that W is in fact this intersection. So the second condition in the theorem I mentioned is also satisfied. Therefore, B is a basis for a topology tau on X. Okay. Next, we are going to show that if we equip X with a topology tau, the topology whose basis is B, then every function f alpha is continuous. Okay, how come that is true? We are going to take any open set U in Y alpha, where alpha belongs to I. Then F inverse of U alpha under F alpha belongs to B by its definition. Again, in this case, M is equal to 1. We take the inverse image of unopened set U alpha in Y alpha. So it belongs to B. And because tau, B is a basis for the topology tau, B is a subcollection of tau, so this set belongs to tau. So this set is open in X with a topology tau. Therefore, f alpha is continuous. Finally, suppose that tau prime is a topology on X such that every function f alpha from X with tau prime to Y alpha is continuous. Then what happens is, because this function is continuous, every inverse image here belongs to tau prime. And therefore, this intersection belongs to tau prime. So every element of B belongs to tau prime. So B is a subcollection of tau prime. Then tau is a subcollection of tau prime because each element of tau is a union of element of B. So it is a union of elements of tau prime. So it belongs to tau prime. Therefore, tau is weaker than tau prime. So tau is in fact the weakest topology on X such that every function f alpha is continuous. Okay. Again, how to define the weakest topology on X such that every function f alpha is continuous or the initial topology on X. Very simple. We take a finite number of open sets in U alpha, take their inverse images under f alpha, and form this finite intersection. Those sets form a basis for the topology tau, which is the weakest topology on X such that every function f alpha is continuous. And each element of tau is a union of elements of B. So it's a union of these intersections. Okay, to better understand this theorem, we are going through an example. And in this example, we consider a family of functions, but there is only one function in that family. So the situation is very simple. We consider the Dirichlet function from R to R given by this formula. F of x is 1 if x is in Q, and 0 if x is not in Q. And the question is find the initial topology on R generated by F, where we consider the usual topology in the codomain R. And since the inverse images satisfy this nice property, we can see that this collection B given by F inverse of U, where U is open in R, is a basis for the initial topology R generated by F on R, the initial topology on R generated by F. Okay, so it follows directly from the previous theorem that this collection is a basis for the initial topology on R on the codomain here generated by F. So in order to determine this initial topology, we only need to find this basis. Okay, so how to find this basis? We only need to find F inverse of U, where U is open in R. Take any open set U in R, then we have these four cases. Based on the formula of the function f, F inverse of U is Q if 1 is in U and 0 is not in U. F inverse of U is the complement of Q if 0 belongs to U and 1 doesn't belong to U. F inverse of U is R if both 1 and 0 belong to U. And finally, F inverse of U is the empty set if 0 doesn't belong to U and 1 doesn't belong to U either. Therefore, B consists of the empty set Q, the complement of Q and R, and therefore tau is equal to B and is equal to this collection because every element of tau is a union of elements of B. So we have found the initial topology generated by F. Again, in this case, there is only one function in the family of functions we consider. In the next video, I am going to talk about the product topology on the Cartesian products of two topological spaces. In that case, we consider a family of functions consisting of two functions. Okay, so that's it for my video on initial topology generated by a family of mappings. Thank you for watching.